Okay, so this is supposed to be some slides here. They're going to just give us an overview of the class. We're going to call this an Introduction to Statistics. So what we want to do here is our rough course outline. So first thing we're going to do in the course is deal with descriptive statistics. That's going to deal with things like answering a question like, what is the average of a set of numbers? You might say, what is the most common number in some data set? I might look at certain charts, graphs, those kinds of things. These are descriptive statistics. We're describing data sets. Typically, I think students find this relatively straightforward and easy. After dealing with descriptive statistics, we're going to move on into probability. Probability, I think some students would say, is the most difficult part of the class. It's not a huge part of this class in general. We could spend an entire year-long class dealing with probability in various ways, probably actually spend a lot more time than that. But we'll do a little bit, just kind of get our feet wet with what's going on there, and then use a little bit of that to deal with inferential statistics. And so this is going to be statistics where we use samples and we kind of guess at what's going on for a population. So we're going to take part of a population, part of sort of what we're considering, and kind of guess at what's happening with the whole thing, because we can't get data for every person or object that we want to consider for whatever reason. Questions here: does the average of the whole population seem to be more than 5 based off of whatever is going on with our sample? You could ask a question like, do blue cars get better gas mileage than red cars? Here we're assuming that we're not going and taking every single blue car in existence and every single red car in existence, but we've got some of them and we measure their mileage and we say, is there a difference in mileage? Something else you could say is, are birthdays distributed uniformly throughout the year? So we're not going to take every person in sort of the world or whatever our population is, it's sort of well defined here. And we're not going to do that with every person. What we'll do is take some, maybe 100 people, maybe 200, maybe 1,000 people, sort of map out their birthdays, see if it seems like things are uniformly distributed. That's our rough course outline. I'm going to give you a better sense of the kinds of things we're going to do here. I'm going to go through some data sets that have to deal with students in this course in particular. So first sort of chart I'm going to show you. I've got a chart here dealing with the first digit of phone numbers of students in this class. So it turns out I can go and look up phone numbers that you list with the college. Some of you do not have a listed number, which so you don't, this doesn't total up to the total number of students in the class. That's fine. Also, this was taken, I think, a little bit yesterday, so maybe there's been a little bit of change in who's enrolled, but more or less this should be correct here. So I get a chart here, and what this is saying is that of all the students that we had phone numbers on the list at the time I checked, there were 20 students. That's 20 here. It's just a number pair to tell me how high this bar is. You could also read off to the left and see 20. So that's the number of students here. So there are 20 students where the first digit of the phone number was a 6. So here I'm including 10-digit phone numbers. So this is really the first digit of the area code. And we had 3 students where the first digit phone number is 7. Now, if you're familiar with various area codes in the area, this might not be too surprising. St. Paul is, and various other areas will have an area code that starts with 651, so that's the 6. Minneapolis and other parts thereabout, I'm not quite sure exactly how that's split up, but they will have an area code that starts with a 6, that's 612, maybe other area codes from other places as well. And then there's some people with 7s. I believe those are some people in Wisconsin. Also, maybe you could get a 763, I think is Northwest Metro, sort of. Maybe we'd sometimes get a little bit of that. But you get some sense of the phone number distribution. That's the first digit of the phone number. Can also go the same way and pull off the 4th digit of phone numbers. So this would be the sort of, you get rid of the area code and the first digit of the next part. This I'm not as familiar with what this means. I'm looking at this data here and I'm kind of seeing no 0s, no 1s, no 8s, no 9s. Maybe that means something, maybe it doesn't. It's kind of a question we can ask later on, is do we suspect that's random based on our sample, or is there actually something going on here where that 4th digit tends to basically never be a 0 or never be an 8 or whatever you want to ask here. So in any case, we had 4 students. 4th digit of their number was a 2. We had a whole bunch of 7s. 10 with the 7th. That seems awfully high here. So maybe it makes me suspect something's going on that makes that 4th digit a 7 more often than not for students in this section for whatever reason. Another chart, we can do the 7th digit. Here, this is getting a lot more spread out here. Note that the vertical axes sort of change here, so the scaling maybe is a little confusing. This goes up to 6. Previous chart went up to 12, so the chart I just showed you sort of after this only goes up to the 6th level. The first one went up to 25, so it's sort of a factor of 2 as we go along. So you can't just go by the height of the bars, but you got to read the axes as well. Here, when we get to the 7th digit of our phone numbers, here, things are a lot more spread out. We didn't get any 1s here. Maybe that's random, maybe that's not. I don't know. I mean, we got 1, 3, 2 at least of everything else. 7 again was the most common number. 5 of those, not that much different than, say, 3 8s, 3 2s. I can get the 3 by going to the left and reading over here. So 3, I didn't put the numbers on top. So it's more data here. One more chart. Can look at last names here, at least according to our directory, and I can count the number of letters in them. So we had 1 student and 2 letters last name, 3 with 3. The most common number of letters last name with 5. We had 9 students that number with 9. Sorry, we had 9 students with 5 letters in their last name. Here. Okay, so there's some charts, and we can start to sort of ask the kinds of things we're going to do with this. So in the first part of the course with the descriptive statistics, first of all, we can create the charts as the example of descriptive statistics. Other things we can do is maybe find the average length of a last name. So we have how many letters in each person's last name. You can look at all those numbers together, and you can create the average. Here, I'm guessing a lot of you are familiar with that. Something that's probably a little less understood right now, though some of you may be quite familiar with this. So we can do a sample standard deviation of the length of last names of the class. That works out to be 2.02 letters. So our average was 5.72. Sample standard deviation is 2.02. We'll talk about these two things a fair amount throughout the class and sort of what they mean in terms of distribution. Something else you can do would be called a mode. I'm not using that word here, but that would be the most common. I chose 4th digit of phone numbers. The section that was a 7. Here. So I was saying that if we looked at 4th digit, that 7 was sort of the most common. That would be the mode. These are all descriptive statistics, things we can do. We're looking at a data set and just sort of describing what we see. Oh, go on to inferential statistics. This I generally find a lot more interesting here. I think it's in some sense the point of the course. Again, this is going to be based on a sample, so that's part of the entire population we're talking about. And one thing that's a little bit weird is if our sample is the students in this section, we've got to determine, well, what's the population? That could be different things. So it's part of a whole. What do we add to our students in this section to get the whole? So one kind of question you could ask is the average length of last name for all students at Century College less than 6 letters? So we view our section as a part of Century College. If you recall, the average length of last names for students in our section was 5.72. So that's less than 6. It'll turn out from methods we have later on that will kind of decide that, okay, the 5.72 is less than 6, but not enough less than 6 for us to be super confident here that the average for all students at the college is less than 6. So we'd sort of say this is an inconclusive question. We'll talk later on about what that means and how to figure that out precisely. We'll come up with numbers here. Next question we could ask, or another example at least, is the average length of last name for all students, say, taking a math course at Century College more than 5 letters? So students in our section are taking a math course. A whole bunch of students taking other math courses, or perhaps students in the section are also taking another math course. And then we can ask, something about the average length of all the students in that population. So our students in our section can be a sample from different types of populations. And in this case, I'm asking, is the average more than 5? So the average was 5.72. Note that 5.72 is further from 5 than 5.72 is from 6. It turns out here that we'd say that there is sort of enough data to conclude this. So we'd say that the answer to this question is that this is yes from a certain point of view, and we'll talk about kind of qualify that a little bit. Both of these questions assume that really our sample is actually a good representation of the whole population that we're talking about. So in the first question, we're talking about all the students at Century College. Second question, we're taking the students talking about only the students taking a math course at Century College. Here's sort of the students in our section in terms of their phone numbers, a good representation of this. It turns out, maybe there may be some reasons why we shouldn't think that's necessarily the case. We can talk about that later on. Something that definitely seems like a bad, or students in our section seem like a bad sample for, but you could make students in our section a sample for the population of all residents or people in the United States. So I can ask a question: are first digits of phone numbers for all residents of the United States distributed uniformly? So I'm just going to go back to our chart here. First digit of phone numbers, we had 20 people with 6s, 3 with a 7. Here, no other digits showed up at all here. And so this definitely does not look uniform. Uniform would be sort of each digit is equally likely, or the bars are all as high. I mean, this 6 is definitely the most common here. So you might go and say, well, it definitely appears that in our sample, then phone numbers, first digit phone numbers are not uniformly distributed. So probably that's not the case in our population. Although in this case, our sample is almost certainly a poor sample for this particular population here, because, I mean, your first digit phone number is generally with your area code, which is based on location. Again, there's only going to be so many area codes near this school, which is going to dominate our students. You may have some totally different part of the country where people's area code starts with a 2 or some other digit. I forget, I think some of the digits probably aren't used for whatever reasons, but definitely the whole country as a whole probably are more uniformly distributed first digits of phone numbers than this chart, at least. Now, is it still distributed uniformly throughout the country? I don't know, but it's hard to make that conclusion based off this data. Okay, so some more inferential statistics examples. So maybe we look at the fourth digit of phone numbers here, and we want to say for all students at Century College, are these distributed uniformly? So I put this chart back up here, scaled a little differently, but it's the same chart. So this was the fourth digit for students in our section. It's a sample of all students at Century College. Do these look uniformly distributed? Probably not. I don't have a 0, I don't have a 1, I don't have an 8, I don't have a 9 at all. I got 10 7s here, so that seems pretty high. Doesn't seem like it's even throughout. One thing that we'll do here in the course later on is be able to attach a number to this. So instead of me having to say, it kind of doesn't really look like that things are distributed uniformly, we'll be able to attach some kind of number in some way that we'll talk about later on and be able to say, yeah, this definitely doesn't. If this sample is a legitimate sample from this population for this particular data, then it definitely doesn't look like these are distributed uniformly. So this one turns out that that's what happens when you run the numbers. Another question, if you look at the seventh digits, so 7-digit phone numbers for all students, say, taking statistics at Century College, are those distributed uniformly? So again, we could think of our section as a sample from the population of all students taking statistics, a smaller population than we discussed so far, but still sort of a bigger part than our section. So do we have seventh digits distributed uniformly? So here's the data from our section. You can see this is 3 zeros. It's somewhere between 2 and 4, and we know it has to be a whole number. So it has to be a 3, 3 zeros, 3 2s, and so on. Now, note this is not completely even. For instance, we got no 1s, 3 2s, 3 zeros. But if you only took a sample of, I think there are 29 here in total, students, not 29, 23 for phone numbers, you're not going to expect this to actually be completely uniform every time you do this. In particular, if you had 23 numbers and you split them into 10 groups by digit, you'd expect 2.3 in each, but if you get a whole number, so maybe you expect 2 or 3, but maybe just randomly there happen to be a lot of 7s. That may not be for any particular reason here. It may just be kind of a random thing. So it turns out when we run the numbers, which we'll learn how to do later on in the course, it'll turn out here that this distribution that we have from our section isn't really strong enough to be able to say that the distribution of seventh digits of phone numbers is not distributed uniformly. So it's kind of an sort of inconclusive result here. We don't really get a strong result out of this. Which isn't that surprising. I mean, this looks, compared to the others, at least the most uniform. Okay, so that's just an idea of the kinds of things we're going to do this semester, give you a sense of what the course is sort of about here.